Okay.
Oh God.
I think we're good. You guys can all see.
Yeah.
I can see. I think that's all we needed. So, we were kind of in the middle of lecture 1.1, and we were talking about the nature of measurement objects. And so we're going to continue on with this. I know that this is it's pretty philosophical, and some of you might like that. Others of you should like that. I realize that this might feel a little dry, this first chapter, but I think it's worth talking about this stuff, even if we do often move on and then say, oh yeah, I remember when we used to philosophize about the different possibilities of measurement. But it's good to slow down and discuss, I think. So, 1.1.2, the nature of measurement objects. Every theory assumes an ontology, which is a theoretical understanding of the nature of being. Okay? Unfortunately, we rarely consider ontology and instead thrash about with some assumed ontology, for there is no theory that does not have at least an implicit ontology. We'll pause at ontology for just a moment before thrashing on, because we really don't have time to get into ontology. But we'll just talk about it for a second. Famous ontologist you guys might have heard of would be Heidegger. So he's very, a Heidegger fan in the back row.
He said ooh.
Oh, I thought you said ooh. And I was like, yes, I agree. Heidegger is pretty great. Yeah, he's Martin Heidegger. He was German. He's considered one of the fathers of existentialism, along with my boy Soren Kierkegaard. But yeah, he unfortunately was too much of a Nazi sympathizer. So we kind of remember Heidegger as being like, ooh, yeah, great ideas. Yeah, and kind of a Nazi though. So.
Probably a little asterisk at the top of his name.
Yeah. History hasn't been super kind to Martin Heidegger, but he was a very. But what it was, it seems, from what that I've read about him, it seems that he kind of sold out because he was comfortable. And yeah, I don't know. There are debates about whether or not he really supported that stuff, or if he just really wanted to remain in the university running the show. So, I mean, I not that we should be like, oh yes, we should dismiss that, but yeah. In any case, people who were alive around that time were very interesting. I always feel like my favorite philosophers and everything were all around World War II.
I mean, you have Winston Churchill, too. I mean, you got some of the big people in that time.
Yeah, very eloquent speakers and thinkers, and yeah, it's a lot of cool stuff happening then. So yeah, I feel like most of my favorite thinkers were writing around that time. So. Okay, anyways, we're really getting off today. So, there are several competing understandings. Remember, ontology is the study of being, right? So, sort of foundational stuff, so being is kind of the basic of all basic things you could talk about. So, there are several competing understandings of the ontological status of the objects of measurement. So, we could ask the question, what is an object that we're going to measure? What is a temperature or something like that? What is a temperature of some object? What does that even mean, really? This guy describes them as concrete individual objects. These are the four possible ones that people usually talk about. So these are the four ones that people argue for. First is that they're concrete individual objects. Okay. That one is definitely the one that's the most common sort of intuitive one. That when we're all, I think, in engineering, we have a tendency towards realism, which we're going to talk about today too. So I think that Some of these other ones are a little harder to get an appreciation for, but some smart people have argued for them. Another one is qualitative observations of concrete individual objects. So the objects that we're measuring, maybe they're not actually like the objects in and of themselves, but they're like the qualitative observations of those objects that we're measuring. Some people say they're abstract representations of individual objects. That's a misspelling, but that is the French way to put it. That is a French spelling. Objet. So it's the, yeah. But there wouldn't be an S. Objet. The,
You only missed one letter.
yeah, it's not so bad.
Yeah, you missed the C in between the E and the T.
Yeah. Jacques Lacan, French psychoanalytic philosopher, really cool stuff that he wrote. He was always talking about the objet a. And I will probably bore you someday with that description of what that is. Okay. And universal properties of objects. So that is another thing that we could be measuring when we measure. But there's not really any universal agreement. We're going to talk about some of these stuff a little bit later, but it's really interesting reads, in my opinion. This is especially important to realist theories of measurement, but it's important to consider in all measurement theories. So when we talk about realism in a little bit, we'll talk more about this stuff. Okay. So we're still on mathematical measurement theory, right? Establishing scales is another pursuit that they are engaged in. So under mathematical measurement theory, quantities and qualities of an object are said to correspond in some way to mathematical objects. So the objects that we're trying to measure, the quantities and qualities associated with them, are somehow related to mathematical quantities, mathematical objects, right? So maybe like a number is corresponding to a length or something. But how do we decide on the mathematical objects, which is the scale? So the mathematical objects that are going to correspond to the objects we're going to measure, that's the scale, so the mathematical scale. What criteria are there for determining the efficacy of the mathematical objects? This is another universal aspect of measurement theories, establishing the way in which scales can be properly established. It is a central consideration of most measurement theories. Okay. Intrinsic and extrinsic. You guys in thermo right now? Yeah. Well, this is a little crossover to thermo. Have you guys talked about entropy yet?
Not yet.
Oh my god.
Class before,
Well,
I know what you're talking about.
I know exactly what you're talking about. We just have talked about it in thermal class this semester.
Oh yeah, I love so great.
Contributing to the heat of the universe.
Yes.
Breath at a time.
Entropy, let's be honest, it's hard to read all of the stuff in engineering textbooks when you're like trying to do all the homework. I read that entropy chapter like very thoroughly. So interesting. I love that stuff. So anyways, this is related to thermo, intrinsic and extrinsic quantities. So there are two ways of putting it: intrinsic or intensive and extensive or extrinsic. I used intensive and extensive most of this place, but in the header I used intrinsic and extrinsic, so that's my bad. I switched. I remember that I was like partway through writing this and I was like, I think I'm going to switch it to intensive and extensive. I think it's a better term, but then I forgot to change the first part. So, intensive quantities are those that represent properties of the constitutive substance of an object. Okay? So they're like somehow, I think you can use the word intrinsic to describe it. Conversely, extensive quality or quantities are those that are unique to each object. And this is approximately how it's used in thermodynamics as well. The quality of quantities, LOL, right? That's funny, I think. The quality of quantities to admit representation by a number leads to a simple manner in which to define the difference between an intrinsic and an extrinsic quantity. If an attribute of an object can be represented by the addition of numbers, it is an extrinsic quantity. Otherwise, it is intrinsic. For instance, weight is best represented by a quantity because combining two objects by an extrinsic quantity, I didn't say which one, that would have helped, right? For an example, it usually helps to actually, use the term in there. Because combining two objects with weights represented by W1 and W2 gives a composite object with weight W1 plus W2, right? Similarly, the densities of two objects, rho 1 and rho 2, if the objects are combined, the densities don't combine by just adding them. If you combine two objects that have different densities, their densities don't just add.
Is this economic class or?
It's not economics. But we could do that. We're accommodating here. I think weight and density are the two easiest to grasp on this stuff. So like, if you're thinking about, you put two objects together, they weigh the sum of their two weights, right? And the new object weighs the sum of the two. But if you have two objects with two different densities, the new object doesn't have the sum of the two densities, right? The density is an intrinsic property that doesn't add to another object's density.
So is that similar to thermo, how some materials and like certain types of steel have intrinsic properties of being able to absorb and transfer heat better than others, etc. In similar fashion.
Yeah. So for instance, the conductivity of an object, that's based on its properties of the substance. So copper has a certain conductivity. But if you put two wires together, depending on how you're defining this stuff, but usually I think it's the conductance is the general property. Conductance is the same because it's still copper, right? You stuck them together, two different copper wires. It's still a copper wire. It's just two stuck together. But weight, for instance, would double or whatever. So it's kind of like that.
And the two densities would only add together if you slam them both into the same volume.
Right.
Which would be very messy.
And I don't know if it would be simply additive even in that case.
Because they could have a chemical reaction with each other and change the density.
Well, if you keep everything else still in the same volume somehow, you're having a constant volume, but you're doubling what's inside. So you double the density as long as the volume remains consistent.
I think you're right. I'm pretty sure that you're right. As long as it's in there and
How do you get in there? So
they actually have to mix fully too, which if it's a fluid, maybe that
Yeah.
could work. But if it's solid,
it's
clearly.
getting it to happen, that's the hard part.
Yeah. So this is, I will say that there's this intensive, extensive is hard sometimes to decide what it is for a certain case. Sometimes it's hard to tell, but that's why I gave you kind of this sort of rule of thumb here where you say, okay, if they add together when you combine the objects, then it's extrinsic. If they don't, then it's probably, it's extensive, otherwise it's intensive. It's the important thing is the first two letters of each of those words, the N or X. Okay. Fundamental and derived magnitudes. So early measurement theories made the additivity and lack thereof of magnitudes the crucial aspect of a distinction between two types of physical magnitude, fundamental and derived. Okay? So later theories, though, distinguish between these two types of magnitude in the following way. So this is the way that we'll use it. Fundamental magnitudes are those that can be measured directly, and derived magnitudes are those that must be computed from a definition that depends on fundamental magnitudes. Okay? For instance, density is measured by measuring both mass and volume of an object, then dividing them, making density a derived magnitude. So you don't measure density directly, you measure the mass, you measure the volume, you compute the density. And so it's a derived magnitude. Does that make sense? Something that I didn't put in here, but you might run into and get confused about is we use the term derived for units, SI units too. So you can have fundamental and derived units in SI. It's closely related, but not exactly the same. For instance, like the kilogram is a fundamental unit in the SI. Fundamental unit in the SI. And the meter is, but like the centimeter is not a fundamental one, and so they have these base units, and that's part of the definition of their fundamental units. That's subtly different. This is about measurement. SI is about defining a system of units. So, yeah, there's a lot to that. They're also about measurement too. SI. We'll talk about SI soon. Sorry, what was that?
The prefixes.
Yeah, like centimeters and.
Yeah, meters. Or gigameters.
Yep. Okay, so this means there's nothing intrinsic about the difference between a fundamental and a derived quantity. Rather, a magnitude that is derived now may become fundamental if a method for measuring it directly is developed, right? So just because density is considered to be a derived magnitude now, because we measure it by measuring mass and then measuring volume, it doesn't mean that there's anything stopping us from developing a way of measuring density directly. And if we did come up with a way, it would become a fundamental magnitude then. Okay? So, of the following magnitudes, which is fundamental and which is derived? And this is a little unfair because you're in a class to learn about how we measure these things. So you don't necessarily know, but you might have some idea. What do you guys think?
One is fundamental.
One you think is fundamental, resistance.
Mass is also fundamental.
I don't know about that one.
I would say that.
I would say
weight is
mass would be derived, whereas weight would be fundamental. Because if we had to weigh something here, we would also have to understand that it also includes
Well,
the weight of gravity.
weight would be a force, right? So mass times acceleration.
Yeah, mass is a fundamental.
So
Well,
mass
how do
is
you
the
weigh?
fundamental.
How do you measure mass without the weight?
How do you measure
You don't
mass?
wait.
Huh?
So like, think about doing a statics or dynamics problem. When you had a force, you'd have to
There's
look
a
at what
standard-
units the force was in, because if it was in
There's a standard for mass.
SI units, you could just use that unit. But if it was in
Because you know what
pounds,
slug is, right?
you have to multiply it by gravity.
Thing is how do you find out what the mass of an object is without the weight? The question here is, can you find mass without knowing the weight?
Yes, that's what a kilogram is.
What is a kilogram? Well, how does SI define a kilogram? Do you know? And then all you need to do is define a gram as 100th of a kilogram, and you're done.
Yeah.
Circular logic.
Oh man.
Probably something to do with Paris.
Yeah. So we're gonna talk about that, but
Bureau of Standards, right?
kilogram used to be based on a certain object that was sitting in Paris.
Yeah, it
That was a kilogram.
Listen at like platinum iridium.
Yeah. And now they've changed. I think that they've converted all of the SI stuff over to theoretical definitions.
Yeah, because it doesn't over time it like
it's really hard to keep them stable.
Less now than it was 100 years ago.
It's much better if you can have a standard that you don't have to have an artifact existing somewhere to be the standard.
That has to be continuously upkept.
Yeah, yeah.
Whenever it loses an atom, it just drops.
Yeah, the bar that they use for a meter, back in like we've used like until 1983, the meter was the length of a certain bar that was in Paris. And then in 1983, they changed it to be like the length that light travels in a certain time interval, in a vacuum.
It's very, very vacuum.
Not your mom's vacuum. Space.
So yeah, so that's what it changed to. But interestingly, it was since like 16 something that we had used that bar. Well, except that they changed it in like 18 something which bar, and I don't know why they changed which bar it was, but I feel like there's a funny story there about when the meter changed in the 1800s, but I don't know why.
I do have a question though.
Yeah, yeah.
because We are debating whether or not which is fundamental, which is derived, and perhaps my understanding is a little bit behind on this, but a fundamental property of something is it's there whether or not, if we say that it's there whether or not we say that it is.
So
a
a realist is in the crowd.
to a certain extent, yeah, but
It's all there whether we say it is or not.
but like this object's weight is different on the moon than it is here.
Mm.
So
And you weigh more when you're closer to the.
right, but the mass is constant. We agree. So that's why I'm saying, like, for example, mass is fundamental to a particular material, whether it's made out of multiple materials or whatever. So I'm just curious as to, for example, mass would be fundamental, at least in my mind, because whether or not we take it to different planets or in space or whatever, the mass stays the same, assuming we're not chipping away at it with atmosphere or anything else.
So I think that you're jumping ahead into the discussion of like the sort of ontological status, like it's there, it exists whether we measure it or not. So we're going to come back to that, but the actual definition that we used, which Campbell was using some more theoretical concepts for it, but what we're using here are that there can be measured directly versus they have to be computed from things we can measure directly. So it all depends on how we measure them,
I see. Okay.
the way we're defining them.
Okay.
But your point right there is going to be an argument for realism, what we're going to talk about very soon. So, but they're all very related, interesting ideas. So, for instance, resistance. Does anybody know how we measure resistance?
Voltage over current?
Yeah, so you can derive it from V equals IR, or you can like just read the little label that says like 5 ohms, like.
But how did they do that?
Yeah.
But then it has a percent error.
So it's.
So they built it with supposed to be 5 ohms, but if we want to measure what it actually is,
We did that.
They use their multimeter.
you use a multimeter, and a multimeter. How does a multimeter work?
Well, it
You
measures the
apply a
other
voltage across, and it
voltage.
measures the current through.
Yeah.
and
Yeah.
does the math for you.
So it
but
divides the voltage by the current, and that's how it knows what the resistance is.
But measuring it directly from our perspective.
Yeah, so I think some of this does come down to like the perspective, but since we built the thing, we know that it's computing voltage over current.
This is like in mechatronics. Where are we setting our ground before
I
we
know.
start doing measurements? Because I'm just like, we can literally do this for the rest of the classroom. Like, so
Everything's based
what
on
is
an
the
assumption.
correct answer here so we know what we're talking about?
Right.
What is our, you set the ground for us, please.
So for resistance, we measure the voltage and the current, and we back out what the resistance is. We compute R equals V over I, which is actually the definition that we gave in mechatronics for the resistance, right? So it is not directly measured, so it's not only equal to, but this is a derived measurement. The paper that I read about this said that it was fundamental, and I was like, no, it's not. Philosophers sometimes don't know how things are actually measured, so. It's like, I don't think you're right on that one, dude. So, yeah, that was frustrating. That was on like the Stanford Encyclopedia of Philosophy. It's just wrong. So, whatever.
Well, they don't know what is going on, and they assume that's right.
Even if
It
you
might
use an
seem
equation
like it
in
is
physics, it's
fundamental.
still right.
The
'Cause you're
smartest
measuring
people in the
it,
world are
but
often
we
wrong.
know what's happening.
That's fine.
Yeah. Well, what about length? So this one is interesting. So what about length? How do we measure length? I mean, we can measure length in a lot of different ways,
We
right?
can measure length with reference to something else, like a cubit.
Right.
Everyone has
So-
feet that
Hands
are
width.
about the same. What makes that a standard?
So length is something that we, like, for instance, with a meter stick or with calipers, you have a measurement directly of the length. I mean, how directly? Is there some ambiguity? I think there is. But they like to make these distinctions in any case. But this one is, in fact, fundamental. You measure directly the length. Something fundamental.
So there doesn't need to be any further calculations, you just read it off.
This is sun-lemental.
Right. If your device gives you that as the result, in the most direct sense, like there's no, and I know there's like, so the multimeter gives you the resistance, so on a really fundamental level, the device, how does it read it, is the
A
question.
ruler has no circuitry. It doesn't have a mind of its own.
Right.
The
So
person that
it's
made it, though,
you're
decided what it
comparing
was.
you're comparing two objects side by side, and the length of one is giving you the length of the other, and so that's why it's fundamental. You're measuring it directly as length. Now you can measure length by bouncing light off of it. That would, that was the only way that we measured length, it would be a derived quantity. But in any case, that's that one. Mass. How do we measure the mass? Something. Well, there are a lot of ways of measuring mass too, but how do we typically measure it?
Okay, we take the weight divided by our gravity constant.
Mm-hmm. So if most of the time, we actually are measuring the strain. Actually, what we measure is like the difference in resistance of a strain gauge in a load cell that is applied, a force is applied by the weight of the object on it, which is just like really removed from the actual mass, right? And then we have to calculate what the mass was. So this one is typically going to be a derived quantity, but there are potentially more advanced ways to do it that we could make it fundamental. If you could count the number of molecules in something, then you could measure its mass directly.
What about on just like a scale where like it tips back and forth? Would that be a direct measurement though?
It's a good question. And that's actually, this is a good point. I've seen people argue that this is the case, that it is. So on a balance, if you use the mass balance, you're comparing directly two masses. And so if you have a kilogram that you know is a kilogram, let's say you know it is.
We went to Paris.
Yeah, you went to Paris, you stole it,
You still have
and you put it on one side of your balance, and you,
Kept it in a vacuum on the way in.
Right.
Wrapped it in bubble wrap, so it didn't lose any.
then you would have yourself, if you had a balance, I think that the balance, I think it's a little bit ambiguous, but I think you would then call this potentially fundamental at that point. Fundamental. Mental. So, whereas Jordan puts the fun in fundamental, I put the mental in fundamental. You like that one? So,
Jam in there.
weight. When we talked about how we measure the mass, I mean, the weight's really pretty much the same thing. I could imagine that you could possibly come up with a force that was a known force from.
Try measuring normal force to calculate weight.
Yeah. I think that in general this is probably going to be a derived quantity, but you could argue it both ways. And part of the reason why we did this is that I think it's kind of ambiguous for some quantities, like which one it is. And really what it comes down to is what you're measuring, how close is it to what you are trying to quantify. So, okay. What about the speed of something, like the radar gun that the police officer is going to get you with on the way home tonight because it's Friday?
That's derived.
Yeah, it's just measuring distance and it's measuring time, and it's dividing them. So velocity is not being directly measured in that instance.
But is time a fundamental measure?
No.
There's an interesting
A
question.
second is calculated by a number of whatever is a particle of whatever somewhere in Colorado.
I think that it's best to continue on in the discussion to the next section, and we're going to get back into this question. So yeah, so let's try to move on, and then we can come back because I think that this is interesting stuff. So there is an ambiguity here that I want to merely suggest and leave open. So let's take mass for instance. So this is the example we brought up. We say it can be compared directly to another mass via a balance, and therefore it is fundamental. However, how do we determine when a balance is balanced? Okay, by measuring, for instance, the angle of the balancing arm, which is surely never zero. So when a balance is balanced, we know that because it's straight across, right? But that's because we're approximating an angle to be zero, which is never exactly zero, so it can only be small enough, and that hints at an issue in our conception of fundamental and derived. I really feel like
That's why we're engineers, not mathematicians.
I feel like there's something fishy about that whole paradigm.
Can you
Close
say the
enough to
same
count.
thing about like measuring something with a tape measure? You're assuming it's zero. Yes.
Yeah.
So wouldn't that be derived then too?
Well, you can count
I mean, I can see your argument for that. I mean, I do really think that you could see pretty much everything as being derived because an actual person has to do it and decide what the reading is to within a certain.
It's like
You could count atoms and use atom lengths.
we have to.
What's the length based on? Like everything is assumption at some point or another. We can't say it's fundamental.
For the same
ever.
reason you can't get 100% efficiency of anything, because you'll never be able to get exactly any given number. So everything has to be derived at some point.
Or we just assume. Velocity is projectile. Exactly.
So let's move on to classification of scales. This I think is kind of interesting. So measurement scales have been classified by the types of transformation to which they are invariant without loss of empirical information. We will consider the following scales originated by Stevens. So the nominal scales are those that are invariant to one-to-one substitution. Those that have no order are quintessential. For instance, gender or concave, convex, innie, outie, navels are nominal scales, right? Like there's not an ordering to the two. Like you just say, oh, innie, outie, male, female, other type of gender. You don't have.
Apparently.
We're realists here.
Yeah, yeah, but there's no natural sort of like ordering of these sorts of scales. There's just like there's a label on this, that, and the other, and they're all like they all have. There's no quantitative difference among them. So that's one scale. An ordinal scale. So ordinal scales are those that are invariant to monotonic increasing transformations. Those that have a specific order are quintessential. For instance, one could feel terribly, poorly, or meh. Another example is physical hardness. So like number 1, 2, 3, 4, up, I think it's the 10. There's no meaning to the interval between two of these, but we all can agree that if you say that you're feeling meh, that's better than feeling poorly. And if you're feeling poorly, that's better than feeling terribly, right?
Yeah.
And feeling terribly is definitely worse than feeling meh.
Yes. Much worse.
So we know there's an order to it, but the amount of difference among them is not clear.
You could say that's relative to
I was about to say
The
it's
person.
all relative to the person.
Right.
My terrible might be your outstanding.
Yeah.
I keep this level every day.
I feel like that was a lyric from a rap song or something. Did Kanye say that? I feel like Kanye said that. If you guys are lucky, one day I will rap for you.
Ooh.
Not Kanye.
Okay, good.
You can't get to that though.
Sorry? What? I missed it. Did I just miss it? Ah, jeez. Interval scales. Interval scales are those that are invariant to positive linear transformation. Celsius and Fahrenheit scales for temperatures are related by just such a transformation. So temperature in Fahrenheit is equal to 9/5 temperature in Celsius plus 32. But temperature in Fahrenheit, temperature in Celsius, they mean the same thing, right? You can transform that quantity to Fahrenheit scale, Celsius scale, means the same thing. And so that means that it is an interval scale, a temperature scale. Well, Celsius and Fahrenheit scales are interval scales. We didn't lose any empirical information. Remember, that was our definition for invariance. And then finally, ratio scales. This isn't exhaustive. This is like most of them, though. Ratio scales are those that are invariant to multiplication by positive numbers. For instance, length can be represented in meters or kilometers via multiplication by a constant, right? By 1,000. Kelvin, unlike Celsius and Fahrenheit, is a ratio scale if negative Kelvin temperatures are excluded from consideration, and they usually are. Whenever a scale admits positive multiplication and excludes negative values, in other words, has absolute zero, it is considered to be a ratio scale. All right? So surely you can have like negative position in terms of like, negative 3.2 meters, but you can't have a negative length, right? So
Just 3.2 meters behind the person or object.
right, so that's a distance, and so you can have a direction that's negative, and that's fine. But length is always going to be positive or zero, and that's why it's a ratio scale. That's why we can turn kilometers into meters, and there's no problem with that. Okay, so classify the following measurement scales. So mass in kilograms. What do you guys think?
Ratio, wouldn't it? Because you can't have a negative number in.
Right. Yeah, so it's a ratio scale, right? Ratio. 2, air quality index.
We should know all about that right now.
Yeah, right? I know way too much about air quality index right now, which is more than 0. I should know 0 about it. That's what I want to know about it.
Is it like the 300s right now?
I've been looking at most of the ones that are like the ones that give names to them, like
Like Mordor?
yeah. But they're like, but there's like unhealthy for sensitive groups, and then like
It's
whatever.
meh.
They take the yeah. But essentially, that's the type of scale it is, right? It's the same. There's an order to it.
but it's relative to each individual person.
Right. It's not clear like what the difference between there is a number associated with it between like a certain number and another number. They just it's just worse. I don't really know how worse, but it's worse. And so that would be an ordinal scale, right? All right, 3. Numbered uniforms 1 through 99. Say you're playing football. Hmm?
Because like the numbers don't have meaning, they're just number uniforms.
Exactly. So they're nominal, right? I mean, maybe people who wear number 1 feel better than the people who wear other numbers, but they really don't have. It doesn't have any significance. So these are nominal. The next one is a time interval in seconds.
Ratio.
So we have a ratio as a possibility. Does anybody want to make another argument?
One way for negative second is time travel.
Yeah, it's
How long you've heard about, it'd be very bad if someone tried. At least for them.
however, you can have negative intervals though. Wait, no, you can't have an interval. You're right, time travel. I think that you're right. I went with I think I did. I went with ratio on this one.
But time isn't linear, so
How many different changes?
this is where we start to get like headaches after watching Interstellar.
We're gonna go full Star Trek right now.
Student.exe is broken.
If you want to argue about Interstellar sometime, come talk to me. I have bones to pick. So
Tell me when that
now is
happens,
not
I
the
wanna
time in class to derail me.
So what you're saying, if we want to
Not
get
the-
distracted, all we have to do
Yeah,
is
it's
mention
mentioned
Interstellar.
Or that other one, Arrival. You guys want to talk about Arrival? Have you guys seen that
I
one?
have not seen that movie, nor have I seen Interstellar
Wasn't
yet.
that good?
Oh man, that one pissed me off. Okay, but it's these ones that want to be super physicsy,
And they're not.
and like what they do is they ruin the story by trying to be like very physically correct. It's like, oh, you mean none of it mattered? Oh, thanks, appreciate that. Now the story is like, oh, it had to be that way. So now it was just all determinism, and we can just stop caring about stories at all because we can't affect them. I guess. Thanks.
Or in The Martian, in the book, he was an engineer with a minor in biology, not a biologist with a minor in engineering.
Oh. Yeah, you can't minor in engineering.
Yeah, seriously.
Well, actually, you can, but
Really?
like you can minor in electrical engineering here, but you practically have to like
Be an engineer.
you have to like almost be an ME in order to be able to do an EE minor. So, calendar time.
That's a ratio because has positive numbers.
you can't have negative July.
I've had a negative July before.
Me too.
So,
Well, can I be like interval because you have BCE and like AD, like ACE, like.
And we're on a Julian calendar. There are other types.
Yeah,
Yeah,
like
absolutely.
Yeah.
Gregorian calendar.
so that's the thing. The 0 doesn't matter, right?
Yeah.
Because there are different 0 dates in different calendars. So the calendar that we're in right now, 0 happened
2017.
2017 years ago, but there are other calendars where it didn't happen then.
In Saudi Arabia, it happened 1,500 years ago-ish.
Yeah, when Muhammad received the
Right.
And then there's this one. I wish that I had my notes with me so I could remember that. It's called the something calendar.
Google to the rest of you.
Disc something calendar.
Is it Discordian, I think? Discordian calendar. Yes.
Next Wikipedia.
It's like a. I mean, I don't want to disparage any religions up here, but it's like a parody religion kind of. Like they legitimately like started it as kind of like a parody, and so their calendar I think starts exactly 10,000 years before or after or something like that. The Gregorian calendar, just to be discordant or whatever. It's funny. I recommend reading the Wikipedia pages about it. But
So are we negative or positive right
Yeah, I was gonna say, would
And
we
also, what is the discordancy?
that is an interesting question that we don't have time to get into. But I recommend reading the Wikipedia page. If anybody decides to convert to Discordianism, let me know. I'm interested to hear what you think. I know somebody who started their own religion, kind of just for fun, and I don't know how serious this person is about it, but I think it's kind of interesting. Yeah,
He lives his life by it. What would you think?
there's a website and everything for it, so I'm just saying.
So wait, where are we classifying this as?
Oh yeah. So this implies something. So the Discordian one has a different 0, right? So it can't be a ratio scale. The interval scale is the one that we have to go with. It's like you can shift it. You can shift the 0 around, and it still means the same thing. Like today is the same in the Discordian as it is in the Gregorian.
Days travels around the sun, whatever.
Yeah.
now? Wait, so is it interval?
So it's an interval scale. So yeah, I should. Right, thank you for helping me to land that plane.
Okay, but Doctor, what do you have against Anne Hathaway?
Oh, nothing. I don't dislike Anne Hathaway.
All right.
I will say that I appreciate Anne Hathaway.